Okay, in this lesson we're going to go ahead and take a look at inversely proportional situations, but I want to back up and compare it to what we've just done. So far we've solved problems where we have two quantities that are directly proportional. And what that means is that as one quantity increases, the other quantity also increases proportionally. So we can set those up as equal ratios, then use our cross multiply and divide skills. That's what we did in our last lesson. And I want to remind you of a situation, two situations. In our first two word problems that we did in our last lesson, we looked at the number of cases of paper and then their weight. We set up a word ratio. In this first case with our weight, we recognized that we had 4 cases weighed 22 pounds. In this case, I wrote weight over cases, so I have 22 pounds for 4 cases. And we cross-multiplied and solved and found that with 52 cases, we have 286. So here we pounds, that is. So here we recognize that our weight increased as the number of cases of paper increased. We did another problem where we were looking at similar figures, where we're looking at the height of a tree and its shadow compared to a man who is 6 feet tall and his shadow. When we set up our ratios here, comparing height to shadow, we could see that the height from the tree to the man decreased from 40 to 6, and the shadow also decreased from 70 to 10.5. And that's what I mean when I say that as one variable increases, the other variable decreases. In this case, we had both variables decreasing. In this case, we had both variables increasing. So each of these are direct relationships. Okay, so what we're going to move into next is very different. We're going to be looking at inversely proportional relationships. And I kind of like to leave that proportional word out of it. A lot of times I usually, invoke variation just to kind of make that a little bit different. So you're not confusing it with proportion skills. As two quantities are inversely proportional if one increases while the other one decreases, or if one decreases while the other quantity increases. So you kind of have one going one direction and one going the other direction. This is an inverse relationship, and so we solve that instead of setting up equal ratios. We set up equal products. And so the best way that I think I can show that to you, where you can really visually see it, is to look at the area of two rectangles. So I drew two rectangles here with their units, and I want you to recognize and see here how this first rectangle, we have a length of 6 units across here and a width of 4 units. And we know that to find the area of any rectangle, we're going to take our length times width. So we know that we have an area of 24 square units here. Okay, looking at our next rectangle here, we've got a length of 8 units and a width of 3. And again, to find the area of this triangle or rectangle, we're going to multiply, and we find that we have an area of 24 square units. So we can see that our area is remaining constant, but our dimensions were a little bit different. So let's look at the relationship between our dimensions. Between these two, when I go from the length of my first rectangle to the length of my second rectangle, you can see that we went from a length of 6 to a length of 8, so we have an increase here. Okay, and then when we look at our widths, we go from 4 units to 3 units, so we can see that we have a decrease here in the number of units. So that's what we're getting at when we say that we have an inverse relationship. So to maintain constant area, we're recognizing that we have equal products, meaning the area, length times width. In order to maintain equal products, we're going to have this relationship between our dimensions. One dimension is going to increase, the other dimension is going to decrease. So that's what we're filling in here, that the area, in order to maintain this equal area, this increased and this decreases. We're going to notice that relationship in quite a few different applications. Oops, so sorry, I didn't have that quite high enough for you to get all that down. Okay, going on to some examples here. We're going to look at the relationship between pulleys as well as our gear. There's an inverse relationship between two rotating pulleys. So we're going to be looking at a term called rounds per minute or revolutions per minute. And we're going to set up this equation here. The diameter of one pulley times its rounds per minute, or revolutions per minute, is going to be equal to the diameter of the other pulley times its revolutions per minute. What I want you to get straight here is make sure that you put the information about one figure on one side of the equation and the information about the other, or the large, I should say. Let's call this the large pulley. Okay, so we're going to see that we're going to go from a diameter of 40 increases to a diameter of 120 on the large pulley. So we have a diameter of 40 here. We're going to see that our diameter is going to increase, and we would assume that to go from here to here with our revolutions, that's going to be a decrease. So we're going to set this up with our calculator. Once we plug everything in, equal products to each other, you can go ahead and, with your calculator, just multiply 120 times 35 and then divide by what's left over here. So you're going to enter into your calculator that data and divide by 40, and you should come out with 105 revolutions per minute. And that makes sense when we look at the pattern here. Our diameters went from here to here, increased. From here to here, we had a decrease. So we can set up something very, very similar when we're looking at the inverse relationship between number of teeth and the number of RPMs on a gear system. Remember, we've looked at this picture before, where we've got quite a few, many more teeth on this larger gear than on this smaller gear. And to maintain that, we know that one's going to have to, if you think about this little gear here is going to have to move around lickety-split a lot faster in order to stay caught up with this thing moving around. So again, organize your information. You can label one side. Gear A is going to be on this side, gear B is going to be on this side, but you're setting up the structure that you're having products for one of our items. The product here is going to be equal to the product on the other item. So we have 48 teeth, and our problem tells us that the gear A with 48 teeth rotated 32 times, and we're trying to figure out how many times gear B is going to rotate if it only has 20 teeth. So we're seeing that our number of teeth goes from 48 to 20, so there's a decrease there. Our revolutions per minute should be increasing. So you'll go to your calculator and you'll plug in 48 times 32, divide by 20. As long as you've set it up correctly, you should get 76.8 revolutions per minute. You can see that that definitely is an increase. So we had a decrease here and an increase here. So you'll notice, very similar to what you were doing with the ratios where you were cross-multiplying and dividing, you've got the scenario that you're going to be multiplying followed by a division. In each of these cases, it's just getting things set up so you know that you are multiplying the correct items. Okay, another area where you use this inverse relationship is called the lever principle. And when I draw this picture here, it's a little bit more of a physics problem than anything. When you have the lever principle basically says that when you have a fulcrum and a beam on a fulcrum, you maintain the balance of that beam between two different forces, two different weights, I should say. If you have a larger weight on one side of your balance beam, it needs to be closer to the fulcrum than if you have a lighter weight item that can be farther away. So you'll have this case of the larger force times the distance, or if you want to call it distance 1, force 1. That product, I'm going to put a little times in here, should be equal to the other force, which is going to be your smaller one. We should just call it 2. And then that distance 2. So the product of these two should be equal to the product of these two to maintain that balance. And a good example of where you might see that is if you go to a park and you see these seesaws. You don't usually see them very often anymore, but the seesaw, the whole concept between the seesaw is that you have this fulcrum, and two kids are going to have to maintain a balance, and they can sit farther out or closer, whatever. But here we have a case where we have two very extreme different weights. We've got a grandpa who weighs 180 pounds, is riding a seesaw with his grandson who only weighs 50 pounds. In order to maintain a balance here, that grandpa's going to have to sit a whole lot closer to that fulcrum than the grandson. The grandson can sit farther out to maintain a balance. So you'll have a shorter distance with a heavier weight on one side of your equation, with a longer distance and a smaller weight on the other side. So we need to set up our scenario here, and you're going to see that you're setting up a shell somewhat similar but yet very different from what we did with ratios. With ratios we were setting equal product or equal ratios. Here we're setting equal products, and then we're filling in the information. So we're going to have grandpa on this side of our data about grandpa on this side of our equation, and then our grandson is going to be on the right side. So grandpa weighs, according to our information here, he weighs 180 pounds. But we don't know how far he's going to have to sit out. Grandson weighs 50 pounds, and he wants to sit way out. He wants to sit 7 feet out from the edge. So we're trying to figure out how close grandpa's going to have to sit. So I want you to catch here that grandpa, the weight is definitely reduced. He's going to have to sit much closer to maintain an increase from grandpa's weight or grandpa's distance to grandson's distance. So you're going to go to your calculator and you're going to say the two numbers that we have together, 50 times 7, and then we're going to divide by the 180. And that should give us, I believe it's about 1.9 feet. So grandpa's going to have to sit pretty close, almost 2 feet here between grandpa and the fulcrum. Another area that you would see work principle is, and supervisors use this all the time, there's an inverse relationship between the number of workers on a job and the amount of time needed to complete the job. And that kind of makes sense. And we've got an example here that we have. Suppose we have a team of painters. There's 4 painters and they can complete the job in 12 hours. How long is it going to take just 3 workers to complete the job? Let's say we had a guy call in that day, and now it's going to makes sense that it's going to take the one fewer worker. It's going to take them longer to get this completed. So our original plan was to have 4 workers working for 12 hours to complete the job. So basically 4 times 12, it's a 48-hour job. But we've got to change this now to 3 workers times how many hours? So you're going to say 4 times 12 and then divide by 3 to get that. Now it's become a 16-hour task. Okay, a lot of textbooks teach this concept, this inverse function, as setting up, how do I want to put this, setting up a ratio where you just flip the second one. And I really want to move students away from that because I think it's too easy to confuse. So what I want you to get out of this is the difference between the two different types of relationships here. A direct proportion, you're going to, the way you recognize that is either both variables, whatever they are, components, either both variables are increasing or both variables are decreasing. That is direct relationship. And when you recognize that in a word problem, you need to keep in mind that you're going to set that up as equal ratios. And you're going to cross multiply and divide. So this is what you're looking for in your word problem. This is how you set it up, cross multiply and divide. You're going to be using proportion skills. Because basically you have equal ratios. So these are all terms that I want you to connect with a direct proportion problem. And when you're dealing with inverse proportion problems, you're going to have one variable, I'm going to slide this up, one variable increases, the other variable decreases. So that's the thing I want you to get out of that. The way you set that up, that's what you're looking for. The way you set that up is you have equal products. So what you're looking for there is your basically justifying that you have equal products. Products means something times something. Okay, in both of these cases, you're going to multiply and divide. That's going to be the order, and you can do that with your calculator. You just need to show me how you've set it up. Show yourself how you've set it up. Either it's going to be a situation like this, if it's inverse, or a situation like this where you're looking at cross products are equal to each other, and that would be a direct proportion.